Let's do another work example. These examples are good to get started with because you're going to see a lot of these types of problems as we go through this course. So we're going to do quite a few that have these piston cylinder assemblies. So let's go ahead and read this problem. We're going to have a gas contained within a piston cylinder assembly. It's going to undergo 3 processes in series. So that just means one after the other. Process 1 to 2 is going to be a constant volume process where we start with a pressure of 1 bar and a volume of 4 cubic meters. And then we're going to go to a state 2 where we have pressure of 2 bar. All right, so our pressure is increasing. Now, the second process, where we go from process or state 2 to state 3, we're going to have compression to a volume of 2 cubic meters. So volume gets cut in half. And during that time, the pressure-volume relationship is given by this relationship right here. Right? So the product of pressure and volume is going to be constant. Now, after that, we've got a constant pressure process where we go to state 4, where the volume at state 4 is going to be 1 cubic meter. All right, so volume gets reduced again. What we want to do is we want to draw the processes in series on the PV coordinates, and we're going to evaluate the work for each process. And we want units of kilojoules. So a few things to do there. So first, let's do the drawing. Look like this. Put your units. So volume is going to go on the x-axis, pressure on the y-axis, like that. And let's start with state 1. So at state 1, we've got a pressure of 1 and a volume of 4. So let's put a 4 here, a 1 for pressure, and we'll put a little dot with a 1 by it. So that's state 1. Now state 2, we know pressure is going to be 2 bar. Now what about volume? So think about what that problem says. We've got constant volume. All right, so constant here is a keyword because that's telling you volume is not changing. So that means volume is going to stay at 4. So we just draw state 2 directly above state 1. Now let's draw a line connecting those two, and we'll put an arrow showing the direction we're traveling. So we're going from here to here. Now we need to look at state 3. So we know our volume is getting reduced to 2. So let's put that there. And we know our pressure-volume relationship is this PV equals constant. Okay. Now, we don't know what the pressure is though, right? It doesn't tell us. So we need to figure that out. So let's do that right here. We do know that the product of pressure and volume is constant. So that means we can write P2V2 equals P3V3. Okay. Now we know the information for state 2, right? Because we've drawn this dot right here. So we know what pressure is, we know what volume is. We also know what the volume is at state 3 that was given to us. That's equal to 2. So we have all 3 of these things. We can use this expression then to find P3. All right, so let's plug in our numbers. So P2, we got 2. Volume 2, we got 4. That's going to equal P3 times 2. Now your pressure, when you solve, it's going to give you 4, and that's got to be bar. Okay, so we need to put a 4 up here. So now we got something like that. So now we can just connect state 2 to state 3 like that. And then last thing is state 4. So we're going to have constant pressure now. So again, constant, there's a keyword. Means pressure doesn't change. And the volume is going to go to 1. So let's put 1 here on volume. This stays right here. So we just need to draw the dot for state 4 to the left of state 3. And then we're just going to draw a line connecting those and draw the arrow, showing that you're going from 3 to 4. So this is our sketch of the processes on the PV coordinates. Okay, so this is the first thing the problem asked for. Now let's go ahead and find the work for each of these processes. So let's start with process 1, 2. And I'm going to do that right here. Okay, so this is where we do the second part. So to find work, remember our equation that we're going to use. We're going to have work equals the integral pressure times the change in volume. Okay, so that is our equation that we have. Now if we look at this one, let's just think about this. We have constant volume, right? Because our drawing goes straight up. We've got constant volume. So if you look at this equation right here, can you have work if you have a constant volume? No, you can't, right? Because there is no change in volume. So we'll write it out and you'll see why if you're not seeing it yet. But if you write out your equation like this, for your limits, our initial volume is 4. And then what's our final volume? It's also 4. So when you integrate, you plug in your limits, you're going to do your function where you plug in 4 minus your function where you plug in 4 again. So that's going to give you a 0. Okay? So work going from 1 to 2 is 0. And it's 0 because there is no volume change. So anytime you have no volume change, you're not going to have work. Okay? So keep that in mind because that can save you time. If you're told it's constant volume, you know automatically no work if you've got these closed systems like this. Okay? So next one is process 2 to 3. So this one we had compression and we were given that relationship where PV equals a constant. So I'm just going to call it C. Now we still need to use that integral equation for work. So we need an expression for P. Now we can get that from this equation here. Let's solve this for P. So we'll get C over volume. And we need to know what C is. All right, and we'll find that in just a minute. So let's just leave this as this for now. And let's go ahead and use our work equation. So this will be the work for process 2, 3. You're going to have the integral. Your limits will be V2 to V3. And then we're going to plug in C over V dV. Okay. Now remember, C is a constant here. We haven't found it yet, but we will in just a second. So you could pull that out. So essentially this is the integral of dV over V. Y'all remember what that is when you integrate that? That's going to be C times the natural log of V. Okay? And then we'll integrate, or not integrate, we'll evaluate at those two volumes. So when you plug these in and subtract, remember when you subtract natural logs, you could put it in that fraction form. So we'll have C times the natural log of V3 over V2. Right. And we'll plug in our numbers in just a second. Next thing we want to do is get rid of this C, because I don't have a value yet. I need a value for this. Now we already said the pressure times volume equals some constant number. We know our values at state 2, for example, so I'm going to say C is equal to P2 times V2. Okay, and then using that, we can plug that into this expression. So we'll have P2 times V2 times the natural log of V3 over V2. Okay, and now we can plug in our values, check our units, all of that stuff. So pressure at state 2 is 2 bar. Okay. And we want the work to be in kilojoules. Okay, so bar is not kilojoules, so we need to work to change that. So first let's switch it over to newtons per square meter. So our conversion for that is 10 to the 5th Newton per square meter per bar. And that gets rid of the bar. And then after that, now we need to multiply by our volume at state 2. So that was 4 cubic meters. And then we have natural log of V3, which was 2, over V2, which was 4, and those units would cancel. All right, so now we're left with this. Now if you look, we've got Newton per square meter times cubic meter, so you're going to be left with a Newton meter. Okay, and the number you get when you multiply all that together is a negative 554,517.74 Newton meters. Okay, now this still is not in kilojoules, so let's go ahead and convert it over, and we'll go through all the steps so you can see. So we need kilojoules. First, let's get it into joules. So 1 Newton meter per joule, and then 1 kilojoule per 10 to the 3 joules, or 1,000 joules, however you want to write it. Let's cancel them out. Those go away, joules go away, leaves you with kilojoules, which is what we want. Okay, so now that's going to be negative 554.5 kilojoules. All right. So that's the work for process 2-3. Now think about what we got here. We got this sign again, this negative sign. That means work is done on the system. So there's some sort of external energy supply or source that is making that compression happen. Okay, the system itself is not causing the compression. It's something external doing work on your system to make that happen. And last one, process 3-4. So this one we have a constant pressure, so that'll make things easy. Pressure is going to be 4 the whole time. So work, you're still going to use this integral equation. Now we're going from state 3 to 4, so you'll have limits of volume 3, volume 4. Put 4 in for pressure, and dV. Now when you integrate, let's plug in our volumes first. You're going to have 2 and then 1 for dV. Now let's integrate. When you integrate here, since you just have 4 dV, you're just going to end up with 4 times volume, and then evaluate at 2 and 1. Okay. Now remember, 4 is in bar. We want kilojoules. So we're going to have to do conversions. So let's do that. We got 4 bar. We need to convert over to kilojoules, just like we did up here. And we need to evaluate at 1 and 2. Okay. So first I'm going to go to Newton per square meter per bar. That gets rid of bar. Then I'm going to go ahead and evaluate at 1 and 2. So we have 1 cubic meter minus 2 cubic meters. Now remember, that gives you Newton meter when you multiply out these units. So now we need to convert from Newton meter to kilojoules. So it's 1 kilojoule per 10 to the 3 Newton meters. Okay, so this is going to get rid of all of these units, and we'll leave you with kilojoules. You're going to get negative 400 kilojoules. So again, this negative sign means work was done on the system to make that happen. All right, because somehow your volume is being reduced. Okay, so some sort of external energy source is being used to reduce that volume while holding that pressure constant. All right, guys, hope you enjoyed that one. See you next time.